Hello again. In our last lesson, we talked about the basic methods of computing probabilities. We focused mainly on just simple events, the probability of an event happening that only has one acceptable outcome, right? So this lesson is going to focus on finding the probability of compound events, the probability of an event that has multiple possible outcomes that would be considered successes. So there's two main types of compound probabilities that we're going to focus on. The first one involves OR events. So this is one that allows a success if any of the specified simple events end up happening. Okay, so an example, I'm going to go up here to the formula in just a second, but just to tie our example in first, if we're trying to find the probability, if we draw one card from our deck, okay, what's the probability that this is just a standard deck of playing cards? Remember, there's 13 cards per suit. There's 4 suits in the deck, a total of 52 cards, right? So if we draw one card from a shuffled deck, what's the probability that that is an ace or a 2? Because those are joined with an or, that means either one of those are acceptable. Now, aces and 2s they won't happen on the same card. They can't happen together. Okay, so we call those mutually exclusive events. If you look at this Venn diagram down here, you can see that there is no overlap between these two sets. No cards are shared. No cards have an ace and a 2 on that card, right? Okay, so essentially, for the more general OR rule, we refer to this as the addition rule because we increase our probabilities when we're finding the probability of an OR compound event, right? So cool thing is you could find the individual probabilities of each event happening, and then we just combine them, add them together. Now, we'll talk about this last little bit of this general formula later, but just keep in mind if your events are mutually exclusive, meaning they cannot happen at the same time, all you have to worry about for this formula is that those first two terms. You just find the individual probabilities, add them up, and you're done. Okay, so let's do some practice with this. So for this example, that means, well, I have 4 aces in my deck out of 52, so the probability of drawing an ace is 4 out of 52. I have 4 2s in my deck, so the probability of drawing a 2 is 4 out of 52. So I'm going to add those up. Notice that this last term is the probability of the two events happening together. We just said they're mutually exclusive events, so they can't happen together. So there is a 0 chance, right? There is no chance that they happen together, so that's just a 0. So again, that last term just goes away when the events are mutually exclusive. And so my compound probability of drawing an ace or a 2 is 8 out of 52, or reducing that 2/13. All right, so mutually exclusive events are kind of nice to deal with. In some of your homework problems, the events will be mutually exclusive. Okay, so let's, I'm going to have you guys complete these next 3 on your own using that example to guide you, okay? So knowing that these are mutually exclusive events, you're simply going to find the probability of each individual event. So for number 1, find the probability of drawing a 3 with this one card, find the probability of drawing a queen with this one card, and add those 2 probabilities together, and that'll get it, okay? So just pause the video right now, do those 3 on your own, and then replay it, and then we'll talk about the the events that are not mutually exclusive. Okay, all right. So hopefully you guys just paused. You've got those 3 problems taken care of. So now we move on. So now, still dealing with OR events, okay? So we still are dealing with that general addition rule, but now this third term, when the events are not mutually exclusive, there will be a third term there. And let's talk about the rationale behind that. So in the case of this example, we're going to draw a card. We're going to see what the probability is that that card is an ace or a spade. Well, if you look at this, those 2 sets do share a card. There is one card that is both an ace and a spade. Okay, and so in our Venn diagram, we show that as overlapping right here in the center. Because of that, note, if we find the probability of each individual event happening, the probability of an ace and the probability of drawing a spade, we can't just stop there because we have counted this overlapped card. We've counted it twice. It's in both of those groups, right? Because the ace of spades is in the ace group, so it's figured into that ace probability. The ace of spades is also figured in that probability for drawing a spade. So in order to compensate so that we only count that ace of spades once, that's where this subtraction term comes into play. And that's just the probability that I draw a card that's both an ace and a spade. The probability that I have this overlapping spot, right? And there's one ace of spades, so that probability is exactly 1 out of 52. And now after I subtract that away, I'll get the real probability of drawing this ace, an ace or a spade, right? So 16 out of 52 is my actual final answer, or 4/13 if we reduce it. Okay, does that make sense? So again, if the events are not mutually exclusive, that means there are some outcomes that are shared between both of the events. Now you do have to do this, you have to subtract the probability of the 2 events happening at the same time, and that essentially means that we're just counting each potential outcome once. No double counting, okay? All right, so now with that example in mind, here's 3 more events that are not mutually exclusive, just to practice your skills. Again, use that example that we did together as a guide, and go ahead and fill out these other ones. So just pause your video, work through these. All right, so now you've done these. I want to do just one more together with you, just to make sure you have that experience and make sure you can check what you just did, see that you are on the same page. So let's do number 6 together, okay? Just to get a handle on this. So remember, our formula then is to find the probability of the first event. We add the probability of the second event. And then we subtract the probability of both of those events happening at the same time. Okay? So let's fill these in. So what's the probability if I draw a card? What's the probability that that card is a face card? Okay, well, there's a jack, queen, and a king in each suit. There are 4 suits. That means there's 12 face cards in our deck. So we have 12 out of 52 would give us the probability for drawing a face card. What about the probability of not drawing a king? Remember the not, that means we're doing the complement of drawing a king, right? Well, how many kings are there in our deck? Well, there's only 1 per suit, right? So there's 4 kings. So how many cards out of our 52 total are not kings? I'll take those 4 away from the 52. We end up with 48. So we have a probability of 48 out of 52 as being not a king. That makes sense? Okay, now what's the probability that those two things happen at the same time? If I draw one card, what's the probability that it is a face card and not a king? Well, how many face cards are not kings? Well, we have the jack and the queen in each suit, right? So and there's 4 suits, so that gives us 8 face cards that are not kings. So we're gonna, and right now, as it stands, we've double counted those 8 face cards that are not kings. So we're gonna subtract 8 out of 52. And what does that give us? Oh, that's an interesting scenario, right? We add and subtract all those fractions together, and we end up with, look at that, 52 out of 52. We have a probability of 1. Go back to the original problem. Does that make sense? Do we really have a 100% chance of drawing a card that is a face card or not a king? Well, if you think about it, isn't every single card in that deck in either one, qualifying in one of those categories, right? Either the card is going to be a face card or the card is not going to be a king, because the not king category includes every card that is not a face card. Does that make sense? All right, so it makes sense that we should end up with a 1 for that number 6. So a good example, an additional one. So with those 2 examples done together, you should be able to confirm whether you're on the right track on number 4 and 5. Okay, awesome job. Now let's change gears a little bit, and let's talk about and compound events. So remember, there was an and piece in our addition rule, right? The probability of events happening at the same time. Now, if we're just finding the probability of an and event, note this is placing more criteria on us for having a success. It's harder to be successful in an and event. So our and probabilities will typically be smaller than the individual event probabilities. Just to illustrate, so before I teach you any formula or anything, let's use our playing card scenario just to get a handle. Let's say we're still drawing just one card. What's the probability that that one card is a face card and a spade? Well, how many cards have both of those happening together? Well, in my spade suit, there are 3 face cards, right? We have the jack, queen, and king of spades. So since there's 3 cards out of my 52 that meet both of these conditions, remember, to be successful, they have to meet all of the conditions if it's an and compound probability, right? Then our probability for this one is simply 3 out of 52. So without any formulas or whatever, we can do the and compound probabilities. You just have to remember, and means all the events have to be able to happen, okay, for there to be a success. For an or, any one or more of the events have to happen for there to be a success. So or is a little bit more flexible and is much more strict. So for 8, what's the probability that the card I draw is a diamond and a queen? How many of our cards are both a diamond and a queen? Exactly one of them, right? And that is the queen of diamonds. So I have 1 card out of 52 that is a diamond and a queen. All right, getting the idea? What about number 9? The probability of getting a heart and a club? How many cards are both a heart and a club? 9, right. So there are no cards that are both a heart and a club. So there's an example where we just have a probability of 0, because those 2 events can't happen together. Hearts and clubs are mutually exclusive events, right? They can't happen at the same time. Therefore, their probability of happening at the same time is 0. Okay, so there's kind of a conceptual understanding of what and is, okay? Now we're going to introduce the actual formula. Okay, so when you're talking about and compound events, either you have a single trial and you want to see if both of those events happen on that single trial, right? Or you could have multiple trials and you want them to happen in a specific sequence. You need a specific sequence of outcomes. So for and compound probabilities, you could write them as A and B, or a lot of times they'll just separate the events with a comma when that's written, okay? Typically when you want multiple trials with a specific sequence of outcomes, that's how you'll see it written. In either case, we're using the multiplication rule for this, okay? When we're talking about the multiplication rule for and, there is a slight notation, a new notation that we need to be aware of, right? So for the multiplication rule, the probability of A and B is going to be equal to the probability of the first event, probability of event A, times the probability of event B given that event A has happened. Note I've given that in a sentence right here on your activity sheet, okay? So that this notation, that vertical bar, means given that second event has happened. Well, what does that mean? Well, the good news is that second term can be simplified if our events are independent. And now this is different from mutually exclusive, so don't confuse these two. So mutually exclusive will apply to our or compound inequalities. Independence is going to typically be tied to our and compound inequalities, okay? But if the events are independent, that means that they don't influence each other. The first event can happen, but it doesn't change the probabilities for the second event at all. So some examples of independent events would be successive die rolls, right? So if I roll a die and I want to find the probability of getting a 2, okay, that's 1 out of 6. That has happened. Now I roll the die a second time. What's my probability of getting another 2? It's still 1 out of 6. My probabilities for that second roll have not changed at all, right? The die starts with all the same probabilities each time. So when we're talking about drawing a card from a deck, that would be the equivalent of drawing the cards with replacement. So that means we draw the first card, then we put it back into the deck, reshuffle the deck, and then we draw the second card. Then we put that back in the deck, reshuffle the deck, draw a third card if that's what we're after, right? So when we talk about with replacement in the context of drawing cards, that's what it means. So that way the deck starts with all of the cards in it in a randomized order every single time. That makes the events independent of each other. So if the events are independent, meaning when the first event happens, the second event still is not, the probabilities of the second event are not influenced, then we can replace that second term in our multiplication rule simply with the probability of the second event. Okay, so these are the more simple versions of the and probabilities, but let's do some just to get a handle on this. So for example, on number 10 here, we have, let's see. All right, there we go. So we're going to be finding the probability of getting an ace. So now we're drawing 2 cards in succession, right? So we want to find the probability that the first one is an ace, followed by the second card being a queen. Okay, so an ace and a queen. What's our chance of getting that specific sequence of outcomes? Well, because our instructions say that this is with replacement, meaning we're putting the first card back into the deck and shuffling before we draw the second card, these are independent events, so I can simply find the probability of drawing an ace and the probability of drawing a queen, and then I simply multiply those together. Okay, so what's the probability that I draw an ace for my first card? How many aces are there? Yeah, there's 4 of them. So that's going to be 4 out of 52. Nice. What's the probability of drawing a queen? Also 4 out of 52. Nice. And again, it's out of 52 because I replaced that first card. Okay. Now I multiply these together, and that will give me the combined probability. I believe, let's see, this ends up, oh, come on. Slide, okay. 16 out of 2,704. I think that reduces to 1 out of 169, or as a decimal, 0.006. So it's pretty small probability. When we're talking having a specific sequence of outcomes happening with successive trials, whatever, the probabilities tend to start getting lower and lower the longer the sequence is that we're after. Okay, so pretty small probability. There's our situation. For independent events, not too bad. Just multiply the probability of each individual event happening. So here's, you get to practice that with number 11 and number 12. Okay, so good luck with those. You'll deal with some larger numbers because you're multiplying things together, right? But once you do the division of the fraction, your probabilities will end up rather small on these. So that's something to be expected. So go ahead and pause, do 11 and 12. And then we're going to jump into that next section as soon as you hit that play button again. All right, so now let's talk about dependent events. So this is where we have to use that more general formula with that second probability with the given that vertical bar in it, right? So now we find the probability of the first event happening times the probability of the second event happening, given that the first one has already happened. All right, so how does this play out? Well, in the case of our card drawing, this would be equivalent to not replacing the first card and then drawing the second card from what's left in the deck, right? So that first card has now affected the probabilities of the second draw because there's less cards in the deck. We assume that the first draw was exactly the card I was after, right? And so that particular card isn't there anymore. So let's look at this in the context of one of these problems. Let's do 13. So now I need to find, okay, the probability of an ace. That's not too bad, okay, because I'm finding the probability of an ace and a queen, right? Now, then I need to find the probability of drawing a queen for the second card, given that I have already drawn an ace, and that card is left out of the deck. That makes sense? Okay, well, the first probability, straightforward. There's 4 aces in the deck. There's 52 cards total, so 4 out of 52. But how is that second probability affected? What's my probability of getting a queen for my second card? Well, there are still 4 queens in the deck, right? I assume that this first ace is gone. It's not there, so there's only 3 aces there, but there are still 4 queens. But how many total cards are there in that deck now? because I didn't replace that first card, I only have 51 cards left in that deck. Again, that second probability was affected because I did not replace the first card. Make sense? And there we have it. Now we multiply these together just like we did before. And we end up with 16 out of 2,652. If we do that multiplication, if you want to reduce that, there's 4 out of 663. I think it's even more meaningful, especially in the context of these smaller probabilities. Let's just convert it to a decimal. And 0.006 is what that rounds to. So note, in this previous example, we had very similar numbers, and the decimal still rounded 0.006. So decreasing this total by one card, even with these dependent events, still gave me a decimal that rounds to about the same thing. So it hasn't changed things a lot. In the fraction form, you can see that the numbers have changed, though. Okay, and depending on the scenario, you'll see a decent difference, right? Because the total number of cards for that second fraction, for that second draw, has diminished, I actually have a slightly higher chance of getting my queen on the second draw, because there's still 4 of them, but now I have fewer cards to choose from. So a greater chance of getting those queens. So if I extended this out more decimal places, you would actually see a difference in that decimal number. Okay, does that make sense? All right, so I'm going to have you guys do 14 and 15 just on your own. Let's look at 16, and we'll do that one together just because that gives us kind of an interesting scenario. So in this case, same thing. I'm not replacing the first card, but I want to see if I draw 2 cards that I get a queen and then another queen. Make sense? So we have find the probability of getting a queen, then multiply it by the probability of getting a queen given that I got a queen the first time. Okay, and didn't replace that, right? So for the first draw, again, everything is just what we expect, right? 4 out of 52, there's 4 queens in the deck, still 52 total cards, but now I leave that queen out that I drew the first time. What's my probability then of drawing a queen the second time? Well, how many queens are left in the deck if I assume the first queen has been drawn? Yeah, there's only 3 queens left. And how many total cards are there in the deck? Only 51 cards total in the deck now. So in this case, where I wanted the same event to happen in succession, now it's diminished both of the numbers in my probability fraction, right? Number of ways I can succeed are less. There's only 3 queens left, and the total number in the deck has also decreased. So just to give you that scenario, I wanted to do that one together. So that leaves us with 12 out of 2652, which is 1 out of 221, which is about 0.005. Okay? All right, so now you're able to do 14 and 15. You have 2 solid examples behind you to help you understand. Again, the second fraction is going to be affected from that first draw because these are dependent events because we are not replacing the first card. Okay, so great experience with compound events. You guys are now ready to do a few more of these with your group. Jump on, make sure you get your questions asked. Have fun with these probabilities.